Hello. Okay, great. So hello everyone. So it's a little bit late for this summit. So thank you for your coming and welcome to the robot world. So most of you guys may doubt how humanoid robot is related to cloud, related to networking and OpenStack. So how could this happen? So yes, actually everything happened for a reason. So let's start our journey and let's figure it out. So I'm from Telexistence. It's a brand new robot startup and founded in early 2018, and it's located in Omotesando in Tokyo, Japan. So if you may travel in Tokyo, you may know that it's Tokyo's it's Tokyo's Champs LC actually. So I'm very excited to work in such an environment full of modern and fashionable elements. So it's cool. So our mission is to industrialize the teleexistence technology, and we wanted to change people's life, organizations, structures, and also finally to change our society. So this is our team, and we are quite international. And we are from, some of guys from Japan, from China, from India, Czech Republic, Canada, Panama, and Sri Lanka, and so on. So it's interesting. And I'm Lima, you can call me Nick, and I'm the cloud architect in this company. And I started with focus on the real-time robotic communication and multimedia and streaming and software-defined networking. So actually, I started to contribute codes and ideas in OpenStack community from 2017. Oh, sorry, 2013. So I'm also the co-reviewer in OpenStack Dragonfly projects. So in this session, I will first explain the concept of teleexistence. So next, I'll provide some basic ideas about why teleexistence technology needs cloud networking, needs edge computing, and how it improves the industrialization of teleexistence robot. After that, I'll focus on how we make use of OpenStack for our products. So first, what is teleexistence? It's a brand new concept, even in robotic world. So it's a cutting-edge technology. So here is a 2 minutes short video. So let's see. Okay, so So what is teleexistence? So maybe you have some basic concept that actually it's a concept that was first proposed in 1980s by Dr. Tachi, and who is our chairman of teleexistence. So and it is a notion of human being in effect being in a place other than where he or she actually exists. and being able to act freely in that remote environment. So actually, these words are from textbook definitions. According to my point of view, telexistence, it enables the transportation of human beings' mind into robot's body, into humanoid robot's body, and while maintaining all the senses from the remote environment. So it's very cool. And in other words, that we successfully make humanoid robot behavior like a human without any learning curve. So in telexistence, there are several main technologies that consist of these ideas, which is first the humanoid robots. Here's C3PO, and we make the similar robots like this. So kind of same scale of the human beings. And the next part is virtual reality, and it enables you to be in an immersive environment. And next is a sensing system, and we capture all the senses from humans' postures, motion, temperature, the environment of temperature and the pressure, vision, sound, tactile, etc. And finally is a communication system. So to enable telexistence in a remote environment, we need to have a real-time communication system or maybe networking system to manage all these data transfer. So in telexistence systems and human in the concept which named a cockpit, and there is another avatar robot which is named a surrogate. So they are all connected through the cloud network. And the cockpit is equipped with a hand controller, haptic display system, body motion trackers, and also the VR head mount display. And all these devices sends the motion data to the surrogate, to the robot, and receives the vision data, sound, and tactile data from the robot. So all the data are managed by a real-time cloud networking system to make sure that they are all synchronized and they are all secure as well. So how can telexistence technology help us? So what's the use case regarding telexistence? So here are several basic scenarios. The first is the inspection and the reception. Now we do not need to human always there to answer your questions, and we can use a robot. And next is remote healthcare. It is a basic use case in hospitals, construction, and machine operations. Is that all? No. And there are two exciting scenarios. Here is outer space exploration. So actually, we do not need to send our astronauts to the outer space, and it's very risky. So we can send our robot, and they don't need oxygen. And firefighting. This is another case that we can enable telexistence to help us. And actually, telexistence is intuitive to help people deal with environment challenges. It can reduce the operational cost when people take risks to fulfill their tasks by deploying our telexistence robot to remote site and let the robot operator work remotely and seamlessly with the remote environment. So it's very cool. So actually, in this session, I don't want to cover all the technologies and the topics around telexistence, and it really takes time to explain everything. So in this session, I'd like to focus on one topic, is how it happens with cloud networking. So this is the core systems in telexistence, and it manages all the data inside the teleexistence system and make sure they are working with it. So actually, there are several requirements of teleexistence for the cloud networking. The first is more capacity and lower cost. It means that there are a lot of data transmitting from the robot to the human, and from the robot to the controller, or maybe from the surrogate to cockpit, and from cockpit to surrogate. So there are a lot of data, vision data, full HD vision data, audio data, and the humans' motions, postures, and robots' temperature and pressure and textile. So a lot of data, large amount of data. And also they needs to be transmitted in a very ultra low latency. So we need to make sure that no matter the robot, where the robot is, and no matter where the human is, and all the data needs to be transmitted in a very ultra low latency to make sure they are always synchronous. So there are some requirements of throughput, requirements of buffering, and lag of interactive content like the textile and the 6 degree of freedom operations. And also the uniform experience. We need to make sure that we can provide the human in a fully immersion and everywhere, and it requires consistent throughput. And even at the cell edge, in the edge computing architecture, it's called cell edge. Okay, so actually the human needs virtual reality devices, which requires a rich version and audio contents, and it requires constant upload, download on all wearables. And this is some basic statistics of the VR system. And usually when we play VR games, basically two-way the telepresence is 5 GB to 25 megabyte, 5 megabyte to 25 megabyte. It's the basic requirements. And currently we are working on the current generation 360 degree videos, which is scaled from 10 megabits per second to 50 megabits per second. But in our next generations is 50 to 200 megabytes per second. Okay, the final is 6 degrees of freedom with a few viewpoints is the maximum, maybe 5 gigabytes per second. So it is a very large amount of data. And next is the dynamic resource allocation at edge. So it is also important is that for all the data are not raw data which pass through the whole system, and we need some operations on each packet, which is some inspections, processings. And for example, we also have some machine learning applications, online machine learning applications for conflict avoidance, motion planning, and health checkup to make sure the robot is healthy, and secure analysis. So there are a lot of applications. So we do need a resource, all the network resources which can be dynamically allocated or delocated at edge sites. And why is the edge? So because here's some data, it's maybe not that precise, but it can tell some problem is that when we say the customer equipment and usually and the latency is around 2 milliseconds. So this is for the cockpit and surrogate, our clients. And to go to the customer premises, it's 5 milliseconds. But if it's a very congested Wi-Fi network, the latency is much higher than this value. And the access network may be this is the edge and the edge compute edge side to the central office, 5 to 20 milliseconds. And the centralized data center is around, from the custom equipment to centralized data center is around 20 milliseconds. But it's not always the case because I work in Tokyo. So in Tokyo, and from my office to the Amazon data center is just around 4 milliseconds. So it depends. It depends on the locations, depends on where you are. So anyway, that telexistence requirements first, immersion must be maintained all the time because we need to make sure that the person feels the same to the robot in a remote site. So it requires the constant qualities of the video, audio, and we need to require that it can be used in anywhere. And from cities to rural areas, reliable network access service, even in some of these challenging environments or cell edges. And also the high mobility, because we need to make sure that to fulfill different tasks, and the robot can move very fast. Like, for example, the robot can work in a car. So to make sure that the head movement is constant. So all these requires the last mile, especially the last mile network. The edge side network should be reliable, provide high bandwidth and low latencies packet delivery. So this is why that also that we need a flexible policy, network policies for packet processing and transmission, and can be dynamically change all these policies. So actually, this is why for telexistence that the edge computing or telco edge architecture is necessary for this kind of application. So currently, we are also work with different carrier service providers and to identify the requirements. And so here is our first demo. I can say demos or demonstrations of our cloud networking system. So actually, we deployed several virtual routers across the Pacific Ocean, and from Japan, South Korea, and to United States or Canada. And we have a global network controller that controls everything. So in this is just basic scenarios. In this scenario that we can to map into a telexistence use case that actually the surrogate, the cockpit, which is the human can stay in the Japan's office, and he can operate the robot in maybe in Canada or maybe in San Francisco. So this is very exciting. So and to adjust all these network policies, and we need network controllers for resource scheduling and for route decisions. And in this networking systems, the source-based dynamic routing is not possible. So because we need to adjust, we need to process all these packets, not just pass through it. So we need our own central brands of network decision. And when we focus on one of the given site, for example, the Tokyo site, actually, we can understand that why the last mile access network plays a vital role in our system. So here is the basic examples. Our cockpit is in one city, and he sends a robot to another city near Osaka, and he can work remotely with the robot in the remote environment. So actually, in Tokyo, we deployed our virtual router instance, but it's not just one virtual router instance, but also along with several virtual network services along the way. So in this example, that we can see that we deployed one packet distributor in Tokyo, and it is responsible for distributing the traffics to different network services, to Nagoya, and to Osaka or to Sendai for different purposes. Some of the network services may relate to the security, and some of related with machine learning resource pool. So the different purposes. So all these services, which in our design will form a network service chain, which is also all the service chain, the deployment of service chain managed by our network controller. So we can see that this network service architecture is actually running behind the scene. So we only see that the cockpit can operate the robot, and the robot can synchronize with the human's motions and postures, but actually behind the scene there are a large network service architecture which support it. So far so good. So let's move on to our OpenStack part. So actually we implemented this cloud networking architecture from scratch, and we borrowed a lot of ideas from OpenStack. Okay, first, and this is our features of the, we can call it the TX Cloud, which is the networking system. So first, the multi-hop global packet transmission network, and it enables intelligent routing, deterministic routing learning, and the dynamic service insertion, and authorization, authentication, accounting. These are the basic features. Also, we apply the soft-defined networking technologies to abstract and to develop our network policy agent for traffic transmissions and for bandwidth control. So also, because it's a global network architecture, so it should limit all the single point of failure, and it should be scaled out. It should be scaled. So, and here the structure of all the basic blocks of our cloud networking applications. So we can see this is very basic blocks. Nothing special. We have the operation portals, and we have some internal services for authentication, authorization, and for resource scheduling, and traffic agent, which is our virtual router instance. And we run our services based on the edge computing infrastructure, on a public cloud infrastructure. It depends on your locations. And we also have a lot of supporting services, like coordination services for the some distributed resources, notification services to send a message, and data persistence. There should be a data persistence services, for example, database, right? And the logging and the program configurations. So these are the basic, I think these are some very basic blocks for a scale-out cloud application. So nothing special. And here is our development plan in 2017. It's an initial development plan, but it makes sense. So we take 3 weeks for analysis, and 6 weeks for design, and 18 weeks for development, and 4 weeks for testing, right? But the interesting thing is here that when we try to implement this whole global network controller with routing capabilities, and it only takes analysis, we take 1 week for analysis, 1 week for design, 4 weeks for development, 4 weeks testing. So it's very, very quick, very efficient. So actually, we save 66% of the development time to implement the first version of our network architecture. So how could it happen, actually? Because of OpenStack. So when we analyze our requirements, and we notice that 60% of the core functionalities have been implemented in OpenStack. There are a lot of, you know that in OpenStack there are a lot of open source projects that we notice 60% have already been implemented. And also additional 50% of the third-party libraries can also be reused from all these OpenStack projects. So That's very cool. And so here is our final implementations of our networking platform and the public service. And we have the operation portals that we developed it based upon OpenStack Horizon. And the core services, we have our OpenStack keystones for managing all the authentication and authorization. And also we extract Nova scheduler to helping us to make decisions on resource scheduling. Okay, here you see that we do not use Nova API, we don't use Nova Compute, only Nova scheduler. And we also do not use Nova placement service. Okay, and for our networking controller, we develop our networking controller based upon OpenStack Dragonflow. It's a distributed network controller developed in OpenStack community. And also for service support and for coordination service, we have OpenStack tools. And for notification service, we have both Oslo messaging and also OpenStack Dragonflow. It has a built-in notification service. And also some third-party libraries and OpenStack uses, and also the OpenStack Oslo. And we use Oslo log to manage all the logs and Oslo config to manage program configuration. So we try our best to fit our architectures to OpenStack, and we figure out that more than 75% of the functionalities has been implemented. So we just use it. And also, I'd like to introduce two very important third-party libraries in our system. First is Kotlin in OpenStack Ceilometer. It's a multi-work framework, and it's the substitute of Oslo service. So it's very cool, and we develop our program based upon Kotlin and etcd3gw, and because we use etcd as the data persistence storage, so we use the etcd3gw in this third-party library from the OpenStack tools and the Dragonflow. So we just use them. And regarding to the core SDN framework, if you guys are working with the NFV and OPNFV or some projects, actually, when I first thought of this framework, the first choice that come up my mind is OpenDaylight. It is a very cool generic network controller framework, and I very like it. But actually, why I didn't use it in my project is that OpenDaylight is very huge. It's a very huge system, and for startup, it's a little bit overkill for our application. And so I decided to use OpenStack Dragonflow. And it's a pure Python OpenFlow controller, because in our system, I'd like to use OpenFlow as a control protocol. So it's a pure Python OpenFlow controller, and it's distributed in nature, and we can scale it very easily, and it has a pluggable application framework. So we can develop our network application, network service upon this framework. And the most important stuff is that it's very easy to remove all these neutron layer 2 logics. You know that in our system, it's more than L2. It's not L2 network controller. It may be L. There are a lot of services around L3, L4, and L7. So we do not need any neutron logics in our system. So in OpenStack Dragonflow, it's very easy to remove them. And also, we need fast processing and real-time response. So, and here is the Dragonflow architecture. I do not like to explain the Dragonflow project, because it's there are a lot of resources, and I will provide here is in Austin 2016, and we have detailed sessions to explain the Dragonflow SDN controller. So, and here are some ideas that when I designed this global networking architecture. First of all is data persistence, so database. And this is very important. And in OpenStack, and you know that we use Oslo DB and we use SQL Alchemy. And we use MariaDB or MySQL systems, and actually record all these database-related sessions happened in the past maybe 5 years or 6 years. Then you see there are a lot of problems on scalabilities of the database. So actually in my system, I'd like to try to eliminate all these problems. So first of all, I choose the inventory is consistent rather than SQL, because it's very lightweight, and I can just use the key value stores instead of all these SQL schemas and data models. And it's only responsible for data persistence, which means that actually in my system, I do not read data from database. I just write data to it. So it's a little bit fancy, and yes, it's true that we do not read data from database. We just write data for data persistence. So how could it happen? Because that we try to, when we design our data modeling, we try to minimize all the logics around the key value operations. Because you know when you deal with key value stores, maybe etcd or other key value systems, and it's just a key value system, and it doesn't provide any data relationships operations, and doesn't provide any transactions. So actually, in our system, I think the key value operation should be as lightweight as possible. So we just write once. When I design all the logics around database, we just write once. And we also read data, but it only happens when the failure happens. So when the system has some failures, and we do need to read all this data from database. So maybe you have some questions around what kind of data we store in database. Actually, it's very simple. It's like Neutron that we store all our network topologies inside the database. But when I implement it, there's no SQL-like operation, for example, join. It's a very heavy operations in SQL system. So we just eliminated it. There's no database relationship. Actually, according to the join, that when we design the key value operations, and the basic idea is try your best not to reference a key inside a key. Do not reference a key from other keys and from other values. So because if you have some reference of the key, then you do need a join. And no transaction primitives, actually. Yeah, this is very important when you introduce some transaction. Actually, there's like etcd, they also provide transaction operations, but it's very heavy. And for other key value stores, if they do not provide atomic transactions, then you do need to introduce some like distributed log managers to manage your transaction to make sure it's atomic in the context. So it's also a heavy operation. So in our database, that I say that so we just write data. If the system operates normally, we just write data. We do not read data. So how it could happen? So because of the message queue. Actually, we implement all our logics around the message queue instead of the database. Because we notice that if we implement our very heavy logics around the message queue, and it can be scaled very easily, instead of we try to implement other logics inside database and database transactions. Okay, for our message queue, and this is for the real-time notification, is that for example, if there are any network service has some changes, or the network topology is changed due to our routine decisions, and we first store all these changes into database, because we write all these changes to database, right? But instead of we calculate all these logics in the database, and after we store all the data to database, we send notifications to the message queue. In other virtual routers, and it just listens on the message queue instead of read data from database. So this message queue is very important in our system, and it provides a real-time notification, and also it guarantees fast delivery as fast as possible, and it implements the message persistence. and implement all the sophisticated logics instead of database. So, and as I stated before, and we use OpenStack Dragonflow as the message queue service because in OpenStack Dragonflow there is a 0MQ based system. Okay, so and virtual router instance. Okay, instead of a global virtual router, and we implement our local OpenFlow controller. Why it is local? Because some of our services needs packetting in. So if there is a one global network controller like OpenDaylight, and the packet in sucks. So we do need an efficient packet in process. And also, if it is local, and we can easily make it stateless. So it's very easy to scale. So anyway, that we have our build blocks from the OpenStack community, and we also write GRUB codes. Actually, all these GRUB codes are also have implemented in all the OpenStack services. Like if you are familiar with one of the services like Nova, like Neutron, Cinder, Manila, all these services, when you go through all the codes, you can notice that all the GRUB codes are similar. So it's very easy to get idea from how to make use of all these codes. So, and also we have a lot of network services, so based upon it, and we develop our OpenFlow applications for each service. So actually, most of our time are spending on how to develop OpenFlow applications instead of how to build all these blocks, because they already existed. Okay, so for summary, and we built our own SDN controller prototype within 6 weeks. Pure Python, scalable, extensive, easy to maintain. And also, OpenStack community provides almost all these blocks that can help us build a scalable cloud application. And also, I'd highlight OpenStack CI can greatly help you identify dependencies and stabilize your system. It's very important because there are a lot of Python libraries, and there are a lot of upgrades of each Python libraries, each third-party Python libraries, and it's really hard to check or to review all these third-party libraries, which version is stable, which is not. So actually, we run OpenStack CI, and it's very easy to identify all the problems. Dependency problems. So, and here is a list that we used in our systems from the OpenStack community. Dragonflow, and we use Lua-based OpenFlow controller, and 0MQ-based message queue, and a database, etcd-based database modeling. And from Oslo project, we use log for log management, config for configuration management, and Stavdor for dynamic plugins, concurrency for synchronization, and tools for distributed log. And Keystone, we use the whole project as our authentication and authorization service. And Nova, we only use Nova Scheduler as our scheduler framework. It is very easy to extend. And Horizon, it's a pluggable web framework. We just develop our operation portals based on Horizon. So, and here are great credits to this awesome open source community. Okay, that's all. Thank you. So, any questions? So, nothing? Okay. I'm sorry? Actually, for us, and we mainly focus on the scalable cloud applications. We do need fog computing or edge computing architecture to support our robot communication. But actually, for us, we are impossible to build from scratch this infrastructure, right? So we work with Huawei, we work with KDDI, and we also discuss these requirements with ATT And in the future, we'd like to work closely with them and for build a scalable and a global robot networking dedicated for robot. So this is what we test. Okay, it's for us. We have a lot of ideas to how to design for a computing architecture, how to explain edge computing concepts. But actually, for us, we are not the company that build it, right? So yeah, I'd like to join discussions around Frog and Edge. That's very interesting. Okay, that's it. So thank you very much. Thank you for coming.